So we got the volume of half the sphere, which we can work out. So pause, copy this. So we work it out, giving us half of what we ultimately want. Multiply by 2, and you are set. You get your volume of a sphere expression. Okay. Now, pause and copy this example. A bit more abstract, I guess. So I'm going to draw a nice picture for you here. Here it is. Whoa! Look at those skills. Okay, so I got the straight line x, and I got the blue curve x cubed. Now I got this banana-shaped region. Where is it? It's this banana-shaped region here. This is my region R. So why don't we label that? Here's my region R here. And I'm rotating that about the x axis here. So you imagine this banana-shaped thing just going around and around and around, or just once, I guess, but and you just got to visualize what it looks like. The full solid you get is not super important to visualize, but I do want you to visualize the rotation of this representative rectangle. Okay, so that's what I'm trying to do over here. Okay, I'll note that here I'm only drawing half of the disk. Okay, but if you go all the way around, you get the full disk. And we will be going all the way around, always in 6.2. Well, we don't get a disk. Sorry, disk is the wrong word. We're going to use the word washer. Okay, this is a disk with a hole in it, right? So in English, we say washer. In French, I believe the word is rondelle. I got a little picture of it over on the right here. There you go. That's a washer. Used in with your nuts or your bolts or whichever, whatever. Not my forte, let me tell you. Anywho, so again, our strategy is to fill the region R with rectangles. Every rectangle corresponds to a washer. You add up the volumes of all the washers you get, and then you let the number of washers go to infinity. Okay, let's scroll down here. I got a copy of my washer here. And I'll let you pause and copy what's on screen now. Down in the right here is just for reference. We'll need this a little bit later. Okay, what's the volume of this washer? Well, we have an outer radius and we have an inner radius. So we have to subtract some circles. Okay, so the area of the face of this face here is a subtraction of circles. And then you have the delta x still. Okay, the delta x is this little thickness here. And the tricky bit is finding what is R0, RO, O for outer, and RI, I for inner. Okay, and for that reason, I have given the original picture down here. Okay, where you can see the outer radius is, which one? This is the outer radius. And the inner radius is this one. So what is the outer radius? Well, you look at this point. You look at this point here. The outer radius is exactly the y value of that point. And then for the inner radius, I look at this point here. And the inner radius is the y value of that point there. Now, this point here, what's the y value? Well, it's on this curve, y equals x cubed, right? So the y value is x cubed. That's what I plug in there for my Ri. Likewise, if I look at the point up here, the y value is just x. So that's why x went in for RO. Okay, the rest is just calculation. I get this expression. And essentially, I'm just sticking an integral in front of it, changing my delta x. Okay, delta is a kind of a normal bit of distance, and dx is meant to evoke a infinitesimally small piece of distance. Okay, because when you add more and more washers, or when you add more and more rectangles here, dx shrinks down to become infinitely small. Anyways, I digress. Let's just finish this calculation. 4 pi over 21. And move on. Okay. All these questions follow a pattern. We give you a region, and then we tell you what the axis of rotation is. Okay, so I'll be stating these questions in that form from now on. So here we have the region bounded by these curves, 4 of them, for 4 sides. I draw a picture. So pause and copy. And then I write down my integral. Now I'm going to skip straight to this integral from now on. It's always of this form. Okay, you have your bounds of integration, which I haven't mentioned yet. Okay, we're doing an integral dx. So as I do this integral, x is going from what to what? Well, it's going, because this is my region here, my x values are going from 1 to 2. Okay, in this case, R0, our O rather, our outer radius, is just the y value of this point. And I have so generously provided that for you right here. So I'm going to be plugging this in for the outer radius. And that's all. You grind it out, and you get 19 pi over 12.